My name is Elliot Slaughter, and I'm here today to present Regent, a high-productivity programming language for HPC with logical regions. This is joint work between myself, my advisor Alex Aiken, and fellow students Wan Chan, Sean, and Mike. Regent is an implicit parallel programming language. Regent programs are subdivided into tasks, which are just functions eligible for parallel execution. Regent can automatically discover dependencies between these tasks based on the original program order in which they're launched and the data usage declared for each task. So for example, in this program, which we can just read from top to bottom like a standard sequential program, we can discover this dependence graph which tells us that all of the B tasks can run in parallel. We can also automate the data movement because the dependence graph accurately captures all of the data movement that needs to happen for each of these tasks to be able to run. And finally, we're going to do this by targeting the Legion Runtime API. Those of you who are familiar with our previous work may note that this list of features sounds similar to what Legion itself provides, so you might be wondering why we created a new language. Well, here's a comparison of code between code written to the Regent language and code written for the Legion C++ API. Obviously, the C++ code is longer, and there's probably a little bit of unnecessary boilerplate in that code as well. But what you have to understand about the Legion API is that Legion requires the user to specify a lot more about their programs than they might be used to doing in other programming models. And in particular, we need to do this in a way that allows the user to achieve maximum performance with their code if they're writing to the Legion C++ API. Regent simplifies this programming model. It provides fewer moving parts and fewer things that the programmer has to think about while they're writing their code. If we wrote a naive compiler for Regent, it would achieve very poor performance. And so in order to achieve good performance, we're going to have to do a number of optimizations in order to recover that performance. But once we have done that, we're going to be able to show that Regent achieves performance which is identical to the original hand-tuned Legion code. But in order to show those optimizations, I need to describe a little bit about Regent itself. Regent starts execution at a main task. And remember that every task runs conceptually in a sequential manner. So we can read the code in the task from top to bottom. Tasks store their data in regions, which are conceptually similar to arrays of structs. Regions have a set of keys or indices which can be used to look up elements inside them, and a set of fields which are stored for every element. And what we're going to do at the level of the system is we're going to have an abstract region tree which represents the relationships between the various regions in order to help with the dependence analysis that we're going to do on every task. In order to achieve data parallelism, we can partition regions into disjoint subregions. And in our abstract region tree, we're going to record one node for the partition itself and one node for each of the subregions under that partition. This tells us, for example, that each of the subpieces is a view onto the parent region, and because the partition that they live under is disjoint, it tells us that each of the subregions refers to disjoint pieces of data. We can continue on with the main task, and tasks in general accomplish parallel execution by decomposing the work that needs to be done into subtasks. And each of those subtasks needs to declare privileges on the arguments which they take to specify whether they read the data or write the data and what fields they're going to read or write. Now let's look at how this actually executes on the Legion runtime. Again, we start with the main task, and we can read the code in the task essentially from top to bottom as if it were a sequential program. So we start with one thread for the main task, and every time we hit a task launch, we're going to launch an asynchronous operation to do a little bit of analysis on that task to figure out where it lives in the dependence graph. Since A is the first operation that we've launched, it has no preceding operations in the dependence graph, and we're going to be able to run it right away as soon as that analysis is finished. If we continue through this execution, we'll see that the B task, each of the B tasks is going to depend on the task A. That means that those tasks can launch as soon as the A task is completed. And we're going to get one B task for every iteration of this for loop. Finally, we have a task C, which depends on all of the previous subtasks. And thus, we have dependence edges from A and all of the B's to this C task. Now, you'll notice that this graph has quite a bit of white space. And that's because in this original Legion program, I neglected to use several Legion features which turn out to be important for achieving performance. The first of those is index launches. Remember that when we do analysis on tasks, we're paying approximately O of n, or O of 1 for every task we need to analyze. That means if we go through a loop with n index launches, or a loop with n task launches, we're going to pay approximately O of n for all those task launches, because they have separate analysis tasks. The Legion runtime provides a way to amortize this cost for certain kinds of loops which are independent and satisfy various constraints. If we transform the loop into that format, then what we'll see is that we get one analysis task which amortizes the analysis cost for all of the tasks that we're launching, and then we're going to be able to launch all of the subtasks as soon as that analysis is done. Let's go back to that original unoptimized code and consider a different feature that I neglected to use in the original code. Recall that tasks can launch arbitrary numbers of subtasks. In general, the analysis that we perform in order to find dependencies cannot be considered to be complete until we know exactly how many subtasks a task is going to launch. This means that the analysis isn't conceptually finished until the task itself is complete, because a task could continue to launch subtasks until it is actually returned. What that means is that any subsequent subtasks at the same level as the original task need to wait for the task itself to finish in order to be sure that it knows about any of the children of that original subtask. The Legion runtime provides a feature which allows users to optimize tasks which don't launch any subtasks. Such tasks, which we call leaf tasks, are a common occurrence in the Legion programming model, and users can mark such leaf tasks in order to ensure that the analysis for those tasks is able to proceed right away. If we look at a timeline which uses such leaf tasks, we'll find that it is quite a bit more dense, because the Legion runtime doesn't need to stall for each task launch, and thus manages to stay off the critical path while the application is running. There is one final optimization which I neglected to use in the original code. Notice that when a task launches subtasks, those subtasks run concurrently with the original task itself. And frequently, those subtasks have access to the same data. That means, for example, that a subtask might read some data while the parent task is writing that data, and this would be a data race. In order to avoid the data race, Legion provides a feature which allows the user to explicitly control access to the regions that a parent task has. And specifically, we have two operations, unmap and map, which control those regions. Unmap releases control of a region to subtasks. So it essentially gives the subtask permission to run with access to that region without fear that the parent task is going to stomp on the region while the child is using it. And similarly, the map operation waits for the child task to complete any operations on that region before the parent is allowed to run again. And this means that the parent must block in order to be sure that the child task is finished. This means that a timeline, the Legion runtime, automatically inserts map and unmap calls around every single task launch if the user neglects to do so. And what this means is that a timeline with these automatic unmap and unmap calls ends up being very spread out because every single task causes the runtime to block before it returns control to the parent thread. Obviously, a user can do a much better job, particularly when the task itself didn't actually need access to the data between every task. The user, for sequences of consecutive task calls with no data access in between, the user can just emit one unmap call at the beginning and one map call at the end and ensure that the runtime doesn't have to block for access to the data between any of the task calls. Now notice that each of these optimizations are features that don't actually occur in the Regent programming model. There are things that you don't need to think about while you're writing Regent code, but in order to achieve performance, we're going to need to perform optimizations in order to make proper use of these features in the resulting Legion code. For example, with index launches, we need all of the iterations of the loop to be independent. In order to determine whether this is the case, we perform a static equivalent of the original dynamic Legion analysis to determine whether the tasks in the launch are going to be independent. And in particular, what this means is that we need to make a static approximation of the original dynamic region tree in order to answer queries about which regions are going to be independent. And in particular, in this loop which acts as P sub i's, we're going to take advantage of the fact that the partition P is disjoint in order to guarantee that each of the iterations is going to be accessing disjoint data. Loops which satisfy these criteria can be transformed into index-based launches, which amortize the analysis cost over the loop. But it's worth noting that and it's worth pointing out that this optimization, while it looks conceptually similar to for all style optimizations performed in other parallel languages, it is actually quite different. And in particular, the only thing that this optimization is doing is amortizing the dynamic analysis cost. It is not finding parallelism in the system, because if the optimization fails, the runtime will continue to find the parallelism regardless, just at a higher cost to dynamic analysis. The only case in which this is actually causes serialization is if it fails in combination with another analysis. And that's something that we'll come back to when we analyze the impact of the optimizations. Similarly, the leaf task optimization requires us to do a structural analysis on the code of each task. The compiler knows whether a task is going to call any subtasks, and we can automatically emit the leaf task marker for tasks which do avoid subtask launches. Finally, in order to optimize the mapping, the compiler is able to perform a flow-sensitive analysis to find spans of the code which use regions in a given mode. For example, spans which give a region to its subtasks, or spans which use that region in the task itself. By emitting calls only at the boundaries between these modes, we can provide mappings which avoid excess mapping and unmap calls between consecutive calls to subtasks, which helps avoid blocking in the application when we're trying to run parallel operations. Finally, we ran several experiments to determine the effectiveness of the compiler and the optimizations that we've described. We looked at 3 applications: a circuit simulation from our original supercomputing submission, which used a reference in C++ in the original Legion API. We looked at PENNANT, a 2D unstructured mesh mini-app with a reference implemented in OpenMP. And we looked at MiniAero, a 3D unstructured mesh code with a reference implemented in MPI plus Cocos. And we did 3 sorts of experiments with these applications. We looked at the number of lines of code to get a sense for how expressive the Regent programming model was. We looked at absolute performance and we looked at the impact of each optimization by performing a series of double knockouts, comparing with each individual optimization disabled and with each pair of optimizations disabled to determine whether there were any interactions between the different optimizations. And finally, we performed these experiments on Certainty, a cluster of machines at Stanford. For the lines of code analysis, we found that the Regent programs were about 25 to 30% shorter than each of the reference codes. What's particularly striking here is that the Regent code for Circuit was about 50% shorter than the reference Legion code. Recall that Circuit was the original Legion reference code. So that, but what's interesting about Circuit is that Circuit also employed manually handwritten SSE vector instructions in order to achieve optimal performance. And what we found was that the Regent vectorization pass was able to recover all of that vectorization performance without requiring the user to write any manual vector instructions. So if we look at Circuit absolute performance, what we find is that Regent performed better than the Legion reference implementation by a couple of % at every node count. This is measuring up on up to 8 nodes running 10 CPU cores per node. If we look at the PENNANT code, what we see is that Regent outperforms OpenMP by about 10% on every core count up to 10 cores. At 12 cores, we saturate the machine, and the Legion runtime threads, which need to perform the analysis in order to find parallel work to execute, start to encounter contention with the application threads. This is especially bad because the application threads tend to have tasks which are long running, and if a Legion analysis task gets scheduled behind one of those tasks, then we don't find parallel work before we need to go execute that work. This results in a performance degradation, which is actually a little bit unrealistic because any actual Regent programmer would just run the 10 core configuration on every node count, on every core count above 10 cores. On MiniAero, we did performance comparisons on up to 10 nodes, and we see that Regent scales well up to 4 nodes. Regent was also about 2 to 3x faster than MPI plus Cocos on every core count. And the primary reason for this difference was that Regent, because it was able to take advantage of a Legion feature to provide hybrid data layouts, which allowed us to take advantage of both SOA and AOS layouts for different fields, which gave us better cache performance. And then finally, we looked at the impact of various optimizations performed. And what's particularly interesting here is that with the exception of a couple of optimizations like vectorization, which had a significant performance on threaded performance, most of the optimizations had very little impact by themselves when disabled by themselves. When looking at pairs of disabled optimizations, when we disabled 2 optimizations at the same time, we found something really interesting. So if you look at each of these graphs, the red horizontal line is the sequential performance. It's the best sequential performance of a Regent implementation on these applications. And what we found is that when disabling, for example, both index and mapping optimization, the code ran sequentially. What this means is that disabling both optimizations resulted in the application blocking after every single task launch, resulting in sequential execution. But disabling only one optimization had minimal impact on the performance of the application. For PENNANT, we found that the application was a little bit more sensitive to the Legion runtime overhead. And so the map and index and leaf optimizations each had about a 10% impact on performance by themselves. When index and leaf optimization was disabled, we saw about a 30% impact on performance, again because we were doing a lot more Legion runtime analysis work, and the failure of the leaf task optimization was causing that work to become on the critical path. And finally, again in PENNANT, if we disabled index and mapping optimization, the code ran sequentially. So in conclusion, Regent is a new implicit parallel programming language. Regent simplifies the Legion programming model so that there are fewer moving parts that the programmer has to think about. And a Regent compiler is able to achieve performance identical to the original hand-tuned Legion code. And finally, and most interestingly, by using redundant optimizations backed up by dynamic analysis, Regent is able to provide robust performance, which does not fall off a performance cliff as soon as one of its optimizations failed. Only if multiple optimizations fail does performance degrade. Thank you.